Thank you for joining us for the 2020 Cutting Edge Virtual Conference, and a big thank you to our conference sponsors. We are pleased to have Mike Mooney and Daniele Nebbia as our speakers for today's session, titled NEBT Project, the Application of Artificial Intelligence to Improve TBM Operations. Mike is the Grucock Chair Professor of Underground Construction and Tunneling at Colorado School of Mines. Mike teaches courses in tunnel design and construction, support of excavations, and civil infrastructure engineering. His research involves pressure balanced TBM tunneling, large diameter liner design, AI and the digital underground, and control of ground and building deformation. Mike serves on the executive board of UCA and is a registered professional engineer. Daniele is a professional engineer with 20 years of experience in the tunneling and construction industry. He is a geotechnical engineer with a master's in mechanized tunneling and has international experience working in Italy, the UK, and the UAE before arriving in Washington, D.C. in 2013. Daniele is the Vice President of Construction at Lane, part of the We Build group, where he currently oversees the Northeast Boundary Tunnel in Washington, D.C., the Ship Canal Project in Seattle, and 3R Port Project in Fort Wayne. I will now hand this session over to Mike and Daniele.
Thank you, Karen. Good morning, everyone. Most of you are familiar with the Northeast Boundary Tunnel. The project is in Washington, D.C., and our client is DC Water Clean River. We are Lane Construction. We've been working with the Colorado School of Mines for the project of artificial intelligence applied to tunnel boring machine. And today we're going to talk about that. This project is 8 kilometers long. You can see that the TBM currently is at 75% of its drive. We pass through some sensitive structure like Amtrak, CSX, WMATA, and other bridges, and is an EPB machine and is doing the excavation for the last 15 months approximately. Next slide, please. So the geotechnical condition of the alignment started with investigation pre-RFP, and the GBR was characterized by all these borehole and the SPT block count and all the samples. But at the end of the day, we are simplifying things and saying that we are talking about two main soil groups, G1, G2, which are the two soil group that we can represent as over-consolidated clay, and G3 and G4, which we simplify calling it dense sand. So most of the alignment we can say is, let's say 2/3 of it is on those dense clay, and 1/3, which is what we are mining in right now, are those sand. The sand will be under pressurized water, will be in, there will be water, there is water, we have encountering water, and therefore it's very important to apply pressure and to mine in a controlled way. Next slide. So we started working with the Colorado School of Mines, and in our project of artificial intelligence, the first question that we asked ourselves is, what do we want to focus on? What are the bigger risks of the TBM that we want to model, control, and predict with this model, with this project? And the result of this discussion was, let's focus on the tool wear, because mechanical damage and potentially catastrophic damages on the TBM can be a very big issue. So we want to try to have a model that is going to predict the tool wear and allow us to make a good decision where we need to do an intervention, when we have to anticipate an intervention or postpone an intervention if it's needed. At the end of the day, what we want is we want to avoid a bigger issue with a TBM stuck somewhere, or with a mechanical failure, or potentially having to have a rescue shaft in a place where we really don't want. So that is something that we want to avoid. And the second part of it, the second thing we're going to focus is the settlement. Of course, creating settlement is something we won't want to do, and minimization of the settlement is one of the targets that we have here. So we we're gonna describe the model that we have implemented to try to predict those settlement. And with that, I'll turn it over to Mike, who is gonna talk about these two items.
Thanks, Daniele. So we have applied AI successfully in tunneling. We applied this to the Seattle North Lake Extension project in Seattle, of course, to detect and characterize the as-encounter ground by the TBM. As we all know, EPBMs or EPB TBMs you cannot see the ground, and so you have to rely on looking at the muck to characterize the ground. We felt the TBM could act as a probe drill and that its performance is impacted, of course, by the ground. So why not use that data to essentially treat it as a sensing TBM? So the way we did this was we trained an AI model using the TBM data and the borehole logs. So that's the borehole logs exist prior to the data, prior to the excavation, and the TBM data is collected while excavating. So we train that model as we go, and then we predict the soil within the excavated envelope through which the tunnel boring machine moves. So here you see the geological profile for the Seattle area, a lot of glacial soil, so very heterogeneous ground. The colors designate different soil units. And then you see the traverse of the alignment of the TBM. What you see here then is if we simply pull out the GBR estimated soil profile, this is what you see: clay, sand, silts throughout the alignment. And then we use the training. And so if we take the data and essentially watch that TBM migrate through the ground, this is the prediction of the ground type. And if you compare the two, again, this is what the TBM mined through. So if you compare the two, you see there's a lot of similarities. So this indicated to us that AI was a successful tool in predicting what the ground type was, simply using the TBM data. So this is really data-driven type modeling. So now if we turn our attention to tool wear, so there's no continuous measurement of soft ground tool wear. There are disc cutter measurements, but that's hard rock tool. There's no for rippers and scrapers. We simply don't have a technology yet that allows us to measure that. And as Daniele said, tool wear is quite critical. So we'd really like to get an estimate of what the rate of tool wear is. So we only get measurements during these limited cutter head interventions, and cutter head interventions in soft ground, pressure balanced conditions in urban environments are a big expense and they're risky. And so they're very limited, and you try to avoid them if you don't have to do it. There are empirical models for forecasting tool wear, but these models are predicting tool wear only based on geology, soil strength, quartz content, D60, which all leads to items like the soil abrasivity index. The TBM operating parameters are not considered in these prediction models. We believe they should be, but there's just lack of data to develop these models. So we felt that AI can help us identify these unknown relationship and specific to a project between the geological, geotechnical conditions or parameters, the TBM operating parameters, and then the tool wear rate. So here's how we did this for an EBT project. So here you see on the left the TBM, and then you see on the right-hand side, this is the excavated ground. In the background here, you see the engineering soil units that Daniele introduced earlier, the G1 through G4. You see the predicted ground type prior to the onset of tunneling. This is done through using the boring logs and geostatistical modeling. And there's some uncertainty in that ground. And the nice thing about this methodology is we can characterize that uncertainty and carry that uncertainty forward into tool wear predictions. So that's the ground type in the background. And then from that, we can predict the soil abrasivity index. So this is soil abrasivity index predicted here. The black line shows the median value of soil abrasivity. And then if you look carefully, you can see shaded regions around that mean that tell us the uncertainty or the variability in SAI that we anticipate. And that, again, that comes from the uncertainty in the geotechnical data just to begin with. So we take this now to train a model. We're going to use inputs from the TBM. So we use the penetration rate, the cutter head torque, the total thrust. These are parameters we believe influence wear or have an influence on tool wear. And there's some other parameters shown there. We also take the soil abrasivity index and its variability, and we use intervention tool wear records to train the model. So you see now in red, we have intervention tool records, I1 through I7, as shown on here. Project is somewhere up here where my mouse is. And so you see that these are very sparse interventions, but for each one of these interventions, we have a record of observed wear. So on the bottom here, you see with a picture of the cutter head, the 8 ripper tools that are monitored. And then in the box here, you see the observed wear. So for example, tool 1 is shown over here with 50% wear. That tool then gets replaced because it has 50% wear. And you see in this particular intervention number 7, all of the tools exhibited 50 to 60% wear and were replaced. And 50% wear, for point of reference, is about ½ an inch or 12 millimeters of wear. So with this data, we trained the model. I'm going to walk you through one example where we train the model over all the data up through intervention 6. That includes all the geotechnical data, soil abrasivity index, as measured TBM parameters, and intervention data. And then we're going to predict then the tool wear beginning from the outset of after intervention 6 through intervention 7 and compare with the results. So if we look at the results, this shows the cumulative tool wear prediction as a function of ring beginning shortly after intervention 6, which is beginning around ring 2700. And you see here, we've got this range or this growth in cumulative tool wear, and you've got this scatter in those results. That scatter comes from the fact that we have uncertainty in the geotechnical parameters. So we don't quite know what the soil abrasivity index is, simply because of the way that we characterize ground on projects. So there is a spread in prediction, but that's a good thing because we can use confidence intervals to predict what the wear might be. You also see the tool wear replacement range from 30 to 50%, which is used by Lane to determine when to replace tools. And here now, let's compare observed tool wear with predicted. So here you see that the measured tool wear has a range to it. These weren't precisely measured tool wear measurements. They were visual observations of wear, so they've got some uncertainty in them. But what you see from this is that the model is under predicting actual tool wear. So that's not a great thing. We want to be spot on with these measurements, or at least within our uncertainty. So possible reasons that lead to under prediction in this case, first of all, the TBM encountered higher abrasive material, G3 and G4, in higher proportions from I6, intervention 6 to intervention 7. I'm just going to jump back here and show that. So between I6 and I7, you see now the TBM is really fully in, almost fully in the more abrasive sandy soils, whereas prior to that, it was in mostly fine grain. So the model's being trained on a lot of fine grain data. There were some areas where it was experiencing coarse grained soil. We felt like maybe that would be captured adequately between I3 and I4, for example. But as it turns out, it wasn't significant or sufficient enough. So that's one reason for the differentiation. TBM parameters were also different, specifically higher thrust on the TBM, higher torque on the TBM between I6 and I7, and that wasn't adequately, its influence on wear was not adequately being captured by the model because it hadn't encountered that ground. So one important lesson from these models is they're only as good as the data. They cannot predict outside the range of the data. So it's really important that the model continues to get improved and updated, and that's the way we've set this up. So what we do then is we take this new data, we retrain the model or update the model, and then we predict the next set of where. And so if you look here now, we see a prediction beginning around just after intervention 7, and then moving for the next 400 or 500 rings. And this is the new prediction incorporating the I7 data and the new TBM data. So this inherently is going to be more accurate. We don't yet have intervention 8 results to compare with this. One note here is we do have lower variability in lower scattering predictions, and that's directly attributed to lower variability in the SAI over this particular range. All right, switching gears now to prediction of settlement. So the TBM-induced ground deformation can be modeled by three-dimensional computational modeling, finite element or finite difference analysis with good accuracy. So here, the inputs, you see a simulation of this step-by-step modeling of deformation here. We actually introduce into the computational modeling the TBM parameters. So there are face pressures, there are grout pressures that are specified along stretches of the project. Those are critically important to predicting the correct greenfield deformation, so we input those. And we found on the project that we have matched the observed greenfield surface displacement profiles quite well using this computational model. So here you see a lot of great instrumentation and data points for greenfield ground deformation. And if you look over here on the right, you see the measured surface settlements and predicted surface settlements line up pretty well on a one-to-one line, which tells us we're modeling accurately using this 3D model. But here's the problem. 3D modeling is complicated and computationally expensive. It takes 2 hours for a single run. So this makes the process of predicting ahead or predicting in real time using construction timescales makes that process difficult. The whole point of this is to use this as a risk mitigation tool. So to be able to predict the next ring, to predict the next shift. And so we need something quicker. So the strategy here was let's train an AI settlement prediction model using all of the simulations. And if the simulations are accurate based on our ground truthing with actual data, then we could feel confident in our AI model. So we trained the AI model using hundreds of simulations, varying geology that we anticipated on the project from the data, varying geotechnical parameters, and varying TBM parameters, specifically face pressure and grout pressure. So we have lots of input. In fact, we have 16 input variables into 800 of these simulations. We ran these on weekends, we ran these at nights, lots of grad students, lots of processors on computers, but completely off of the critical path of the tunnel project. So it just churns away and produces all of the ground settlement data we need to then train this AI prediction model. So in theory, the settlement predictor is as good as the computational model, and it can predict in seconds now. Now we've got a tool that, if given inputs, can predict what the settlement will be in seconds instead of hours. So the AI model shows similar capability as the computational model in successfully predicting ground settlement. Here's a good example where we've got a longitudinal displacement profile at this station 20 plus 93. And you can see here the red dots are the observed measurements, about 0.7 inches of maximum settlement. And then if we look at a transverse profile at section A there, you see that the AI model matches the FDA model, the finite difference model, and as well the measured results. And then there's another station just here, 27 plus 10, where we see a similar successful level of modeling. So now we've got a settlement prediction tool, and we're going to apply this for the rest of the project, always continually training this. So what you see here is about 4,000 feet, 5,000 feet of tunneling through urban environment, as shown on the top Google Earth type picture. And then we have the prediction every 1,000 feet or so, we make a prediction as shown in this graph. So as an example, at station 230, we see a prediction of what the maximum settlement will be. Again, there's variability in these estimates because the ground conditions are variable and we don't have certainty in what they are. And the TBM parameters are variable too, and there could be operator error. We always have to capture, we want to capture potential operator error. So what this shows is the max settlement can vary. With 95% confidence, we can say the max settlement will not exceed 1/2 of an inch. So that's good information to have. We can't say if it's going to be between 0 or if it's going to be 0 versus 1/2 an inch, but we can say with 95% confidence it's going to be at 0.5 inches. So finally, though, limitations with this approach, these are greenfield ground deformations. These are not structural deformations. So we have lots of training data on greenfield conditions. In order to develop an AI type model for structures, you need lots of different types of structural deformation, different types of structures and data. So that's much more challenging. However, we all understand that buildings are, for the most part, stiffer than the ground, and so deformations of the ground will be less than the greenfield. So there's still a lot of value in that. Secondly, one of the challenges is adequately capturing the geological features in an AI model. And so this certainly is a work in progress. And as we move forward in our study on the NEBT project, as we get new data, we'll be able to update our model predictions here. So with that, I'll turn it back to Daniele for some final thoughts.
Thank you, Mike. So some conclusion and final thoughts. Obviously, for us, having been the contractor in Anacostia, which was the previous project for DC Water, was important because we had a lot of material, a lot of data, and you know, the more you know, the better is the model you create. So that was one of the reasons why you know, we involved also Colorado School of Mines, and we got focused on the NEBT. We decided, like we discussed before, to focus on toolware and settlement because they are related to the higher risk on the TBM in the urban area. And I think we got good results. So right now, one of the challenges that we had, as Mike described before, is the availability and the quality of the data to be able to train the model. So one of the things I see in the future becoming important is having some sensors, some means and methods, some ways of capturing more information to be able to better train those models. So as I said, overall, we are very happy. I think we got good results, and now we are ready to go to the next phase where we can actually make decisions based on the recommendation that we got from this model. And I think we can focus on try to anticipate or postpone interventions and you know, improve our quality and our productivity as well. The second part, which is related to the settlement, we can look at the consideration and the suggestions from AI and decide if we want to change some parameters to even further reduce our settlement. As of now, the machine is proceeding with very little settlement. There will be a presentation during this conference with a colleague of ours that is going to describe a little bit. But generally speaking, we are pretty happy. And in conclusion, I want to say that it's not only about predicting and focusing on one project. The importance of creating this model is also related to capturing some of the data that in the future we'll be able to train more and more model and make it more universal, more applicable to different contexts as well. So with that, I conclude, and thank you for your attention.
I just wanted to also give a shout out, thank our team. Rajat, Hatian, Jarrett, and Hongji have done a lot of great work on the project and helped prepare the presentation.
Wonderful. Thank you so much, Mike and Daniele, for that informative and engaging presentation. Mark your calendar for more professional development opportunities. Mind Exchange SME Annual Conference and Expo takes place virtually March 1st through the 5th, 2021. RATC 2021 will be held June 13th through the 16th in Las Vegas, Nevada. And join us here again for the Cutting Edge Conference, November 15th through the 17th of 2021 in Dallas, Texas. Join us in celebrating the 2020 UCA Award recipients. UCA is proud to honor industry excellence in the following awards: Lifetime Achievement, Outstanding Educator, Outstanding Individual, and Project of the Year. View this awards program on the conference site of ucaofsmecuttingedge.com. It's more important now than ever to stay connected. Find the right connections with UCA. Renew your membership today. Job seekers and posters can now access the new UCA Career Center. Visit tunnelingjob.org to learn more about this industry-specific career job board. If you're down for that, help us inspire the next generation of engineers. Learn how you can help introduce underground construction to students at undergroundcareers.org. This concludes our session of the NEBT project, the application of artificial intelligence to improve TBM operations.